This is a video from my Calculus 1 Exam 2 review. Recall. Hyperbolic cosine squared of x minus hyperbolic sine squared x is equal to 1. So what I'm going to do is divide both sides by hyperbolic cosine squared of x. So this is what we get when we do that. We get hyperbolic cosine squared x divided by hyperbolic cosine squared x minus hyperbolic sine squared x divided by hyperbolic cosine squared x. And that's equal to 1 over hyperbolic cosine squared of x. So 1 minus hyperbolic tangent squared x is equal to hyperbolic secant squared x. So we're going to need this shortly. So what I'm going to do now is set y equal to the inverse hyperbolic tangent of x. Solving for x, we get x equals hyperbolic tangent of y. Differentiate both sides with respect to x. And when I do, I get 1 equals hyperbolic secant squared y times dy dx. So dy dx is 1 over hyperbolic secant squared y. Okay? But recall, let's go back to the previous page. Notice that 1 minus hyperbolic tangent squared of y is equal to hyperbolic secant squared y. 1 minus hyperbolic tangent squared y is equal to hyperbolic secant squared y. So therefore, dy dx is equal to 1 over 1 minus hyperbolic tangent squared y. But in the beginning, we set x equal to hyperbolic tangent y. And so therefore, dy dx is equal to 1 over 1 minus x squared. And so therefore, the derivative of the inverse hyperbolic tangent of x with respect to x is equal to 1 over 1 minus x squared. Now, with that in mind, let's take a look at number 25. On 25, we want to find the derivative of y equals x times the inverse hyperbolic tangent of square root of x. dy dx is equal to, so I'm going to write down the first function, which is x. I'm going to multiply by the derivative of the second function. The derivative of the second function is 1 over 1 minus what's inside that inverse hyperbolic tangent, which is square root of x, squared. But by the chain rule, I have to multiply by the derivative of square root of x with respect to x, which is 1 over 2 square root of x. And then I'm going to go plus the inverse hyperbolic tangent of root x multiplied by the derivative of x with respect to x, which is 1. So if we take this a step further, we get x times 1 over 1 minus x times 1 over 2 times the square root of x plus the inverse hyperbolic tangent of root x. And so I'm going to go a little bit further here. I can write this as square root of x because x divided by the square root of x is square root of x squared divided by square root of x, which is square root of x. So I get square root of x divided by 2 times 1 minus x plus the inverse hyperbolic tangent of root x. Like so. And getting a common denominator, I'm going to take the second term and multiply the numerator and denominator by 2 times 1 minus x. So when I do that, I get the following. I get dy dx is equal to, now I get square root of x plus 2 times 1 minus x times the inverse hyperbolic tangent of root x. That's the second term. And then I'm going to divide by 2 times 1 minus x. And that's how we do this problem. And let's take a look at number 26. Now, in 26, it says to evaluate the limit as t goes to 0 of, we get t cubed in the numerator, and we get tangent cubed of 2t in the denominator. Okay, first, let's recall a few things. The limit as t goes to 0 of sine t divided by t. Well, that's equal to 1. So, therefore, the limit as t goes to 0 of t over sine t, I claim that's also equal to 1. Okay? Now, let's focus on a piece of this. I want to look at the limit as t goes to 0 of t divided by tangent of 2t. Okay? Now, I can write this as the limit as t goes to 0 of t times cotangent of 2t, which is the limit as t goes to 0 of t cosine of 2t divided by sine of 2t. Now, notice how the argument for sine is 2t, but I only have a t up here. I want the argument for the sine to match this factor right here. And to accomplish that goal, I'm going to multiply it by 2. But to multiply that t by 2, I have to counterbalance it. And I'm going to multiply the limit by 1/2, because that's like multiplying by 1. Okay? Now, let a equal 2t. As t goes to 0, can we agree that a will also approach 0? right? And the way I'm going to write this is 1/2 the limit as a goes to 0 of. Now I get a cosine of a on top, and I get sine of a on the bottom. Now, let's go back. So remember this, the limit as t goes to 0 of t over sine t, that's 1. Well, I have the limit as a goes to 0 of a over sine a. So if I just focus on this piece, as a goes to 0, that will go to 1. And so what I have left is 1/2 the limit as a goes to 0. Well, let's do it this way. Let's go on the next page. So I'm going to break this up a bit, and I get 1/2 the limit as a goes to 0 of a over sine a times the limit as a goes to 0 of cosine a. So this is 1/2 times 1 times 1, which is 1/2. And so therefore, the limit as t goes to 0 of, and then let's remember it's t over tangent 2t, is equal to 1/2. Now, here's the neat part. All I have to do is cube both sides. So I'm going to raise both sides to the 3rd power. And so what that tells me is that the limit as t goes to 0 of t cubed over tangent cubed of 2t is equal to 1/8. So I'm applying a limit property. And that'll do it for this video. And we did problems 25 and 26. Thank you.